Okay, well, thanks very much. It's a pleasure to be here, and obviously it was a pleasure to be in Stockholm. And I must say, along with Serge, I think we both feel this is, it's wonderful to be recognized this way, but it really represents more our field, and it could have been, certainly in my case, many other people to receive the award besides myself. Certainly, I'm indebted to my colleagues that I work with, but there's a very large number of people throughout the world working on this problem and these kinds of problems, and so it's really a very large enterprise these days. So let me. I'm going to repeat a little bit what Serge said. I won't say so much about this, but except to say that I think one of the interesting things, Schrödinger, who of course was one of the inventors of quantum mechanics, was bothered by the fact that although you could think in terms of the simple Gedanken experiments where you're considering a few elementary particles and the ideas of a superposition and entanglement, the problem that he brought out and was bothered by was the fact that if you take quantum mechanics to its large-scale limit, you get these bizarre situations like Schrödinger cat. And so anyway, so that was certainly what motivated him in his thinking, and it's the world we can start to explore now. So just as a kind of an illustrative tool, what I find that interesting is this example that was in this book here by Alan Wolf, and I think for the non-special it gives a pretty good idea of superposition and also measurement. So if you think about Serge showed this anagram, which is similar in nature, but another picture of this is to think about this box here, and if you, of course, you can look at it with different perspectives, so that either this surface is in the foreground or this surface is in the foreground, like this picture here. And what's interesting about this analogy is that in some sense it represents superposition, because in some sense the box in this view here has both properties simultaneously. That's the superposition. And what's interesting too is if you look at this, at this box here, at some instant you can maybe see this surface be in the foreground, like here, or vice versa. And this idea of where you tend to see the image be either one of these two possibilities is like a measurement. That is, you're projecting into one state of the system versus the other. And the other thing is that, well, anyway, so the idea is that, when we do a measurement, we collapse or project the system in one of these states or the other. So thinking about entanglement, at least if you'll play along with me here, at least for my own situation, if I look at these two boxes here, I tend to, if I see this surface be in the foreground, I tend to see the other surface be in the foreground. And similarly, if I look at the other surface, I tend to see this correlated view of the pictures. And this is very much like an entangled state. That is that in this situation here, we have a superposition of both states being with the foreground and on one square or the other. And I think this gives a kind of a useful picture gives the flavor of both superposition and entanglement. So coming back to Schrödinger's cat, in his example, this is an entangled superposition. That is, we have a state that we represent as a superposition of the correlated states of the particle undecayed and the cat alive, and at the same time a superposition with the particle decayed and the cat dead. So one thing about this, Schrödinger was bothered by this idea that, well, if you take the natural, extrapolate the quantum mechanics to its to a large scale, you get to these situations like Schrödinger's cat, which is very very non-intuitive. And one way out of it that he posed in the 50s would say, well, these Gedanken experiments we can think of with very small numbers of systems, you know, we can't really do that. You know, we can't experiment with single electrons or atoms, and you know, we can do this with thought experiments, but if we extrapolate it up, it leads to ridiculous consequences. But of course, as we know now, the kind of experiments Serge and our group and many other groups around the world are doing is that we can play with these small systems. So we can get to these situations that they were thinking about in these Gedanken experiments. What it requires, of course, and this is where the technology was needed to get to be able to play these games with small numbers of particles, is that, you know, we need precise control. We need to isolate as best we can from the environment, and of course they can become more easily seen in small numbers of particles. So we need to get down to these very small systems to start to be able to see these effects. So when I'm going to describe you similarly to Serge a little bit, it's historical and it's a bit of a personal story how I got into this business, and but of course, again, you want to keep in mind it's the work of many other people besides myself and Serge. So this was actually, I was a student, graduate student with Norman Ramsey, and this is a picture of his group in '66. This is me here trying to get close to the boss. That's Norman Ramsey there. And anyway, it was at a time when he and Den Kleppner had recently developed the hydrogen maser, and so my thesis project was to build a deuterium maser. It had some technical differences, but basically Norman wanted to get the accurate measurement of the hyperfine frequencies of all three hydrogen isotopes. So I always muse over the fact that I'm probably the only one in the universe that has this number memorized. But anyway, that was the main result of my thesis. What it did teach me, of course, was to think, you know, start to think about precise control of systems in a precision frequency measurement. You have to consider this whole host of systematic effects that can perturb the result that you get. So you know, it's good training to be thinking about all these systematic effects, environmental effects that can perturb the frequency. The other thing is, of course, in a maser system, you're looking at radiation of a superposition state. And in that case, we were getting, although it was an ensemble, a large ensemble of atoms, we were getting superposition states, so we're living on the order of a second in this maser system. Okay, from then, after I got my degree, I went on to Hans Demold's lab, who was interested in or pursuing both trapped ions and in that case, during that time when I went to his lab, he was most interested in electrons. So what you can think about is that the trap, which I won't say much about, you know, a useful analogy is to think about a marble in a bowl that's rolling back and forth. And what we do in the lab is in these experiments on electrons that I was involved with, you can we apply electric, and in this case it was electric and magnetic fields, but what you can think about is that the electron in this case is a harmonic oscillator, much like the marble in the bowl, and we have some electrode structure which provides this atomic-sized bowl, you might say. The other thing is we can think about this as there's an equivalent circuit that describes the electron and its harmonic well in this trap, and so we can make an electrical equivalent of this electron or ions in the trap. And what we do to get an idea of how many in this case electrons are in the trap is we put this this equivalent circuit in a simple circuit here where we have an oscillator that we tune to the resonance frequency of the tuned circuit, and we can measure the current in this the oscillating current in this equivalent circuit, in this simple circuit that I show there. So what we did, we were trying to get down to single electrons, and so in these experiments here, what we did is we drove this electronic circuit just to the point where the electrons in this trap were at such an energy that occasionally they'd gain through a collision process, for example, that they'd get enough energy to strike the electrode and therefore exit the trap. And you can think in the marble analogy, it's just we're right at the edge where the marbles want to roll out of the top of the bowl. But anyway, we could get a picture like this. And when we got down to this last step here, that indicated that we had one electron in the trap. And of course, this was part of the process in getting down to these small systems to be able to isolate single systems, in this case electrons. Of course, this was part of the work that led up to Demoult's Nobel Prize, where he performed a very accurate measurement of the electron's magnetic moment. So at the same time when I was a postdoc there, we were starting to think about ideas of cooling, either in this case, we were thinking in the context of atomic ions, and the reason that was important is that also to get control over these small systems, we'd like to get down to the very low kinetic energies of the ions or electrons that to be able to get down to the quantum region of motion eventually. And the first step in that direction was to this idea of laser cooling, and Demoult and I had some ideas, and it's at essentially the same time Ted Hench and Art Shallow were thinking along the same lines. The pictures we had at that time looked a little different, but in fact they're basically equivalent. So at that time, after finishing my postdoctoral work, I went to the National Institute of Standards and Technology, which was then called the National Bureau of Standards. And my first task was to make the cesium beam, that version of the cesium beam work. And fortunately, at that time, NBS was more of a service organization. There wasn't really much research going on, we had to. Our mission was to provide time in terms of the second, which is defined through the hyperfine frequency of the cesium atom. But my boss at that time, Helmut Helvig, was very forward thinking, and he was able to convince the higher powers to give us money to start these laser cooling projects, and he realized, of course, they had applications for clocks. So anyway, we got the resources to pursue this laser cooling. And just a little bit of history. Peter Toshek, he collaborated with Demoult, who went there to Peter Toshek's lab on a sabbatical. And they were also, Demoult and I, as I said, were thinking about these ideas, and so they wanted to pursue this. And this is papers that came out almost nearly simultaneously. You notice our paper came out a little earlier than their paper, but to be fair, you can see that they submitted their paper one day earlier than we. So I guess you'd have to say they were first. Actually, what was interesting about this for me, I actually knew, because I knew Demoult had gone there to work on this laser cooling, but I think they didn't know about us, and so it's a striking near coincidence that in fact we got the results at basically at the same time. At that time, the experiments were pretty crude, and but what we could show from my experience of looking at currents in electrodes, like the electron experiments, in the experiment of Peter Toshek and Demot and their colleagues, the evidence was just that they could if they invoked the laser cooling, they could see it indirectly just because of the ions would stay longer in the trap. In our case, as I say, having had this experience of looking at induced currents, if we looked at the thermal currents, that were induced in the electrodes, those are basically proportional to the temperature, so we could get a direct measurement of the temperature, and the results weren't too startling. We could basically determine that we had cooled down to less than 40 Kelvin, but at least it was a start in this direction to be able to cool down the energy. So this is a picture of our group at that time. There were only 4 of us, and you'll of course notice that some of us have shown our age a little more than others. My colleagues Wayne Natano and Jim Berquist pretty much look the same, but some of us seem to get older over this time. So anyway, from there, following the ideas, we wanted to be able to start to cool down the motion to get better control of this system. But also, as with the electrons, it would be nice to get down to single ions. So the first experiments on that, actually, Peter Toshek and again Demot were the first to get down to single ions, and they actually made some pictures. This shows a picture of a single barium ion. Barium is interesting. I should say most of the ions we work with, because one electron is a move from the neutral atom. The relevant transitions are in the ultraviolet, although for barium it's actually in the blue part of the spectrum. And in these experiments on barium, you can actually see a barium ion, a single barium ion, with your eyes. In our experiments at about a little later, we were also again looking at these induced currents. In this experiment, rather than driving and this was on magnesium, rather than driving the magnesium out of the trap, we used a charge exchange process, which allowed us to see these steps in fluorescence, which indicated individual ions. And of course, the interesting case is when we got down to this last step and we had a single magnesium ion in the trap. So we at that time we were to explore this world of getting down to these quantum levels further. One of our favorite ions was mercury, and for mercury, the transition that we use for cooling. If you're unfamiliar with cooling, basically you want to do is you want to take an allowed transition and tune the wavelength of a laser slightly below the resonance frequency. That provides the cooling. Thing that was hard about, or at least technically hard about this experiment, is the wavelength we needed was 194 nanometers, which was in those days a real feat. And then Jim Berquist, my colleague through all of my career, he's the laser expert in our lab, and he was able to make a CW source at 194 that allows us to do these experiments. So what I show here is this represents the electrode structure, which I'll come back to in a minute. But one of the reasons this mercury ion was interesting is that there's a transition also in the near ultraviolet from this ground S level to excited D level. It's excited by a quadrupole transition. And the lifetime of the D level here is about 1/10 of a second. Why that's interesting potentially for frequency standards, of course, is that with this relatively long lifetime, the Q, or the line width of this transition, is very narrow. That would allow us, if we use this as a reference then for a clock, then that would give us very high precision on the being able to control the frequency of the clock. So at that time when we started these experiments, we really couldn't technically think about optical transitions for clocks, but we were looking ahead towards that possibility in the future. Anyway, one of the things that was interesting to think about was you know, what if you consider this three-level system, what happens, let's suppose if you leave this laser on that does the cooling, we also can see the ion through the fluorescence. And the question was, well, what happens if we also turn on a laser here that induces this transition? And there was some minor controversy among the experiments before, among the theorists, excuse me, before these experiments were done, which was, the question was, well, how would this fluorescence appear if we induce this transition and occasionally put, you know, if the ion has some amplitude up here, does the fluorescence sort of gradually decrease or uniformly decrease, or and of course the real answer was we see discrete jumps. Either the ion you know, fluoresces due to this transition, or the fluorescence completely disappears when it's promoted to this level. And in fact, the answer was it does this switching behavior. We see it either fluoresce or not fluoresce. So at that time, for fun, we made a movie of this fluorescence. So you'll have to bear with me. This was a pretty crude movie, but anyway, it shows the first picture you'll see is these electrode structure mounted on a U.S. penny, about the same size as your smallest coins. And in this second version, the pictures get worse here, but you can still see this kind of donut-shaped electrode in one of these so-called end caps. And then the last picture is taken with a crude ultraviolet camera, and you can just barely see the outline of this donut, the inner part of the donut here. And what we do is we slowly turn in this 194 nanometer laser onto the ion. You can start to see the ion glowing here, and we're going to gradually tune closer into resonance. So you see the fluorescence increase, and as we get closer to resonance, you more clearly see the fact that as the ion changes into this D level, the light will suddenly switch off and the ion blinks, showing the presence of these quantum jumps. And this is, anyway, that's a simple, at least a little bit clearer picture of the situation there. Of course, you know, one thing that's interesting here is you know, the size of the atom is actually a few hundred times smaller than the image we see, which is of course limited by the diffraction limit of the optics. Okay, so we can, with those experiments, we can see certainly the quantum nature of the internal states of single atoms. And so what about the motion? To get more into the quantum regime, we want to be able to get down to the quantum levels of motion. So again, the classical picture is the marble in the bowl, but we know at the quantum level, our marble, or our atomic marble here, is a harmonic oscillator, and so it has discrete energy levels, much like the photon states in the cavity of Serge Hirosh's experiments. So what we wanted to be able to get down is to these smallest energy levels, the ground level, and the first few excited states. Of course, one difference is we have the energy splittings of these levels compared to these levels about a factor of 10 to the 8 smaller, so we get down to a much smaller energy scale. Nevertheless, we could start to get into the regime of playing with these quantized oscillator levels. So what we do is what you want to think about here is that if we take this laser and tune it around the resonance frequency of this transition, and then what the data shows down here is that we alternate these two lasers. So we apply this laser for a little while, and then we turn on this laser. If the ion is promoted to the excited state, we see the fluorescence go away, and that's what these dips represent here. So if we tune this laser to a frequency where the motional state in the the ground electronic state is the same as the excited electronic state, then we would see this feature here. We could also see what we call sidebands. In this case, this is a transition where we not only change the electronic level, but you can see we change the motional quantum state by 1. And this picture that I'm drawing, it also works, say, for the n equal 1 to n equal 2 level, have the same resonance frequency because of these equally spaced levels. And we could also look at the so-called the red sideband here, and see this feature here. So this was a way to start to see, we could see the quantum levels by this separation of these energy levels. Now, what was interesting, of course, was to think about getting down to the situation where we could freeze out the motion. And so the way we were able to do that is to cool the motion is that we rely on the fact that, first of all, that after exciting the ion to this upper level here, when it decays, for the conditions we had to a very good approximation, when the atom decays, that its motional quantum number doesn't change. It decays back down to the ground electronic level without changing the motional quantum number. So we could, the way the cooling worked then is that we would apply this, tune the laser here to the red sideband such that when we excited the electronic state, we would reduce the motional quantum number by 1, and then when it decayed, it would decay down to a lower emotional level. And the basic idea then is we'd leave the laser on continuously, but this process would repeat, so that eventually we'd come down and we get down to the ground state of motion. And the way we could verify that we had the ground state of motion is that if we tried to drive the transition, this red sideband from the ground state of motion, of course we can't drive the transition. There's no level for this to go up here. So it was this on a magnified scale. When we got down near the ground state, then this feature here that would correspond to the absorption of a photon while reducing the motion, it would disappear. And so this asymmetry in the sidebands was an indicator of the fact that we were in the ground state. Of course, we weren't perfectly there, but the fact that this sideband was so much different, it said that we were predominantly, each time we tried the experiment, we'd be in the ground state. So anyway, coming back a little bit to the clocks, this is a lot of development went in, and Jim Berquist in our lab was the primary person on to try to develop optical clocks, and this was a long process. We had this idea in 1981 that this would be something we could go for, but there was a lot of development in over the years, and it was only in about 2005 where we were able to make a clock, an optical clock using Mercurians, where the performance of the clock was actually better than the best cesium standards, and that really signaled a change in accurate clocks, where we went from microwave transitions to the optical. And at least for all the high accuracy clocks now, all of us think about optical transitions rather than microwave transitions. So let me say a little bit about quantum information. This has become a popular topic since around 1995, and actually, some of the early ideas were due to Richard Feynman, David Deutsch, Paul Benioff, for some of the early, or people think about some of the early ideas. And it was sort of these were kind of toy ideas at first. Actually, one of the things Richard Feynman was thinking about is knowing how hard it is to simulate a many particle system, the quantum mechanics of a many particle system. Basically, you need an exponential the resources scale exponentially with the number of particles, and with on the order of even 20 particles, you know, a normal classical computer can't handle can't store enough information because of this exponential scaling to do computations. So that was really Richard Feynman's contribution. But these, you know, the technology wasn't there to even think about actually making a useful device. But what happened in around mid-1990s was that Peter Shor, a computer theorist, came up with the idea that if you could make a computer that would rely on quantum principles, he showed that he invented an algorithm for factoring large numbers. And I think many of you in this audience know that reason that's interesting is basically all encryption that we use, for example, in our credit cards. The security of the encryption relies on the inability to factorize large numbers. So this had immediate applications for you know, security agencies, intelligence agencies, and so this certainly kicked off a lot of funding for these ideas of quantum information processing because of this implications for security. In the atomic physics world, actually, I think almost all of us were ignorant about these first ideas when they came out. But actually, Arthur Eckert, who is already a accomplished person in terms of quantum communication ideas, he came to a conference in Colorado, a major conference for atomic physicists, and gave us a talk on about these ideas on quantum information processing, quantum computing. And at that meeting, two prominent theorists in our field, Peter Zoller and at that time his protege Ignacio Serac, heard this talk by Arthur Eckert, and they you know, I must say, to their credit, they not only excellent theorists, but they also pay attention to what the experiments could do, and they were certainly aware of what the atomic ion experiments could do. So they really jumped on this after hearing Arthur Eckert's talk. They jumped on this, and they were really the first ones to propose a model for how you might, a comprehensive model for actually how you might make a quantum computer. So in the ion world, the basic idea they came up with is, let's suppose here's a 5-qubit quantum computer, just to give you the idea. Anyway, so the idea they came up with is that, so the qubits, the quantum bits, would be based on internal states of some atom, and these could be the optical states, like I showed you for the clock. That could be hyperfine states. The key point is that we want to isolate two energy levels in the internal energy levels in our ions, and use those as quantum bits. So I'm just changing the notation here a little bit just to distinguish from these motional states. Anyway, their idea was the following: is that consider that with the abilities of laser cooling, is that we're going to take this array of ions, which you can kind of think of as a pseudo molecule, and with laser cooling, we're going to, based on the ideas I presented before, we're going to freeze out all the modes of motion and put them in the quantum mechanical ground state. And then what you can think about is that, say, take one of the modes of motion, we can isolate them spectroscopically because in general they have different frequencies. So the simplest one to think about is the center mass, where all ions might be oscillating back and forth together in this trap, the bowl for the atoms. And the reason that's interesting is that their idea was that, well, if we can think of some way to take the internal state superposition and then map it onto a superposition of the ground and first excited state of one of the motional modes. The reason that's interesting is because each mode has a component in all the ions. In other words, it acts as a data bus for the experiment. So the basic scheme they came up with was that to be able to map the internal state superposition of this, in this example here, this qubit onto the motional mode, and then if you could somehow make a gate, a quantum gate between this motional qubit and the internal state of this qubit here, then basically you've done a gate between these two ions here. And to give you a flavor of how this can work, let's come back to it. Let's assume that our internal state qubit is this an optical transition, and let's assume we've mapped the first qubit's superposition onto the ground and first excited motional mode, or motional states of a particular mode. Then to get the flavor anyway of how a quantum gate might work is, let's suppose we call the motional states here as forming what we call the control bit, and the internal states, we'll call that the target bit. Then what we want to just demonstrate in this simple example is that if the control bit is in the n=1 state, then the internal state will change. And so the way we can accomplish that is thinking back to the diagrams a few slides ago, is that if the motional state is in the n=1 level, and if we tune to the so-called red sideband, then we can actually adjust the strength of the laser and its duration such that when the ion is in the n=1 ground state, then it makes the transition up to the excited internal state. So that that's this part of the truth table here. On the other hand, if the ion is in the motional ground state, then when we apply this laser, there's no level to go up to here, so the ion stays in the internal state. It stays unchanged. So this gives kind of the flavor of how we make quantum gates. It turns out this is not. There's some problems with the way I've described it here, but it's based on this sort of the fact that we can't drive transitions from reduce the energy below the ground state, and it's, even though the gates we use are actually a little bit different, it's based on this simple idea here. And in fact, we had been thinking after these first laser cooling experiments for the ground state, we were thinking of how we could play games combining the motional and internal states. Anyway, we were able to, Chris Monroe, who was in our group, and at that time we were able to immediately jump on this idea of Ignacio Serac and Peter Zoller and basically demonstrate the key part of their scheme, that is the show a quantum gate between the motional qubit and the internal state of an ion. And certainly I must say, Peter Zoller and Ignacio Serac, they really gave a great stimulus to atomic ion groups throughout the world, and today there's over 30 groups just pursuing these ideas based on pursuing quantum information. And at the same time, I have to say there's a number of groups pursuing quantum information with atoms, and also now electronic circuits, Josephson junctions, and so it's a huge industry right now, this idea of trying to develop an information processor based on atoms or other quantum systems. So coming back just to kind of help complete the story, we could, at that time, we could think about a simple kind of demonstration of Schrödinger's cat. So the kind of experiment we could do is we put a single ion in the trap. We would put it in the ground state of motion. Then what we would do is we'd start the atom in its electronic ground state, and then what we'd do is we'd create an equal superposition state of the ion, so a superposition of both the ground and excited state. And it turns out with laser beams we can use we can arrange things using what called optical dipole forces to apply a force to the ion, but a force which depends on which internal state the ion is. It's basically, these forces are based on the light shifts, the so-called Stark shifts that lasers can induce on atoms that Serge uses in his experiments. In any case, we could realize a situation where there was when we applied these dipole forces, the force would only exist on what I'm labeling as the spin-up state here. And what we could do then is we could basically kick the spin-up part of the wave function, and so the spin-up part would start to oscillate. And then we would flip the spin, so we'd change both spins from up to down and down to up here, and then we would apply the force again, this optical dipole force, but maybe with a different phase, so that we could realize a situation where the atom on the at some instant of time, the atom on the left would be on the left side of the bowl, correlated with the spin being down, and also on the right side of the bowl correlated with the spin being up. And this we would say is very analogous to Schrödinger's cat. The analogy being that the microscopic property, say in Schrödinger's example, this particle that is decayed or not, we're saying that's whether the spin of the atom is up or down. The magnetic moment is pointing one way or the other. And the more macroscopic property, the cat being dead or alive, is the more macroscopic property of the ion being on the left side of the bowl or the right side of the bowl at some instant of time. So anyway, when we did this experiment, well, this just shows a little bit of the schematic. We did it on beryllium ions, and you'd have to say this was a very small cat, but in the sense that we could only separate the parts of the wave function by, in this case, about 8 times the size of the wave packet of the atom. And kind of a funny comment came out later. Well, this letter to the editor was by this fellow. He says, well, even kitten seems to be too macroscopic to really, talk about Schrödinger's cat. And he said, well, why not call it a fur ball? And the reason I like this comment is that what he's saying is, well, it's just too small to really call it a cat. But on the other hand, if you say it's too small, you have to say, well, what's the dividing line? Where's this? What's the extension of the ion that we need to call it really a cat? And I think one of the interesting things is we don't know the answer. That is, in principle, there's no reason we couldn't make the separation of the parts of the wave function much more macroscopic, which you might more easily accept as being like Schrödinger's cat, and that is more classical in that sense. And what's interesting is that we really don't know where the dividing line is, and so that's one of the interesting questions, I think, for the future. So let me just say, try to condense down a very large amount of work, this 30+ number of groups, but let me just say well, what's going on. I give credit to my co-workers here. Didi Leibfried, who has been with our group over 10 years now. He certainly some of the simple algorithms, kind of like subroutines in a computer, we've been able to demonstrate, and Didi Leibfried in our group has led a lot of that. One of the things that number of groups are thinking about is to, I've talked about these optical dipole forces that can excite oscillatory motion of the ions in the trap. You can think of these as these oscillating ions as being like electric dipoles. Well, the electric dipoles can mimic also magnetic dipoles that are coupled together. And so one of the things a number of groups are thinking about is to mimic spin system magnet, in other words, coupled magnetic dipoles, which are describe a lot of condensed matter, to use the electric dipoles to mimic those systems, much in the same way that Feynman and others were talking about. And anyway, this just shows an example in our lab. John Bollinger he uses a different kind of trap for ions, but he can make hexagonal arrays, and mimic these magnetically coupled systems. And this is interesting because you can get into so-called magnetic frustration and there's some interesting properties in terms of quantum phase transitions for those. So a number of groups, including ours, is trying to get to these to start these simulations. And certainly, the best control of any of the ion groups is achieved by Rainer Blatt's group in Innsbruck, and they've effectively, I would say, they really made the first quantum computer in that they can take arbitrary algorithms in terms of the gate operations, and although the operations are pretty simple, they really have made a sort of a universal quantum simulator in their experiments, still on a handful of ions. And so even though right now the kinds of experiments he does and other groups are doing that we can efficiently simulate on a classical computer, we're getting to the point where I think we can think about getting to the point where we get to a large enough system that we can't simulate it anymore on a classical computer. So, and of course, in addition to those people, there's many more. Let me just say, come back to this. What we've used is some simple ideas in using these quantum logic ideas to make a clock. And one example there is where another ion where it's interesting for an optical clock is aluminum. We could detect the transitions in the same way I described for mercury. The problem is that this is at such a short wavelength, we don't have a laser for that. So what we do is in this experiment is we put an aluminum ion in the trap and a magnesium, in this case, ion in the trap, and we can use these ideas. I mentioned in the Serac and Zoller scheme for quantum computing is you want to first map the internal state superposition onto a Mosen superposition. Well, here we use that idea, but then we for one mode of motion of this pair of ions, we can then map the motional superposition onto the magnesium ion. And the reason that's interesting is that we can then easily detect using this second laser transition which states the magnesium ions. So this is a way to detect the aluminum ions that was impossible because we don't have the detection laser for the aluminum ion directly. There's some other advantage here, I won't go into all the details. But anyway, we're down to the point where we can, where the systematic uncertainties in these clock experiments are at the level about of part in 10 to the 16. Or part in 10 to the 17. I won't have time to go through here, a little movie here, but what we did in this for fun was we had 2 aluminum clock experiments. This shows one of them on an optical table, and what James Chow here, a postdoc in our group, did is he raised the table by 33 centimeters, and the interesting part of this is what we can actually see the gravitational potential redshift that Einstein predicted, and we don't measure it with any very much precision, but we actually can can see if we raise the clock by about 33 centimeters, we can actually see this, the shift in frequency due to the change in gravitational potential as predicted by Einstein. So I'll conclude here quickly. I'd like to acknowledge the members of our immediate group, but of course, as I said before, it's a huge number of people. In our group over the years, we've had over 100 students, postdocs, and visitors that have contributed to this work, and we've had great institutional support. I'd like to acknowledge our laboratory director, Catherine Gebbe. She, in her tenure of about 20 years, she now has, with including myself, now 4 Nobel Prize winners. So she's someone who's really to be commended, and of course, a lot of support from the agencies. And one nice thing for me about the award is that Serge and I have been friends for about 20 years or so, and certainly our wives are friends as well. So it's been really nice for that reason as well. So thanks very much.
So thank you very much for this comprehensive talk. We are running a bit late, so I think we can only have a single short question if there is some burning. Yes?
What was the biggest breakthrough for this work? Which part was toughest, most difficult to work out?
I don't know if there's any single thing. I described to you some of the steps, the isolating single particles, the cooling, and that sort of thing. So I know people often like to think about some eureka moment where we, had a big breakthrough. But I think it just, certainly in our case, it was a number of smaller steps that led to where we are now. So, and a lot of hard work by many people.
Okay, so we are getting close to the end, or we are at the end, but we are also getting close to Christmas, and therefore I want to give you a little gift as thanks for visiting Uppsala, and so you remember us.
All right, well, thanks very much. Thanks a lot. Thanks for coming too.